Chapter 7, Think and Explain. Number 58. Why does one get tired pushing against a stationary wall when no work is done on the wall? All right, so this gets down into macroscopic versus microscopic work being done. Even though you are not doing any work to the wall, your work is being done at a cellular level. So you are straining your muscles as you're doing it. Muscles do move back and forth. It takes energy in order to get them to move. You're tensing up because you're not, when you push against the wall, you're not relaxed when you do it. At least I'm not. 65, you watch your friend take off in a jet plane. You comment on the kinetic energy she has acquired, but she says she experiences no such increase in kinetic energy. Who is correct? This is the case, actually, you're both correct. Kinetic energy is based upon mass and speed. And in classical physics, mass doesn't change with speed, although it does in modern physics or semi-modern. But the speed is based upon the reference frame. So whenever you're looking at conservation of energy or conservation of momentum, you really should specify the reference frame. Now, typically, the reference frame is that of Earth, but it doesn't have to be. And so the friend's speed is 0 and stays 0, just like there's been some part of my body that has never moved my entire life, and just the world has moved around it. And what is the dog chewing on right now? Okay, a bone. Now, number 66, a jumbo jet slows and descends on approach to landing. There's a decrease in both kinetic and potential energy. Where does this energy go? A lot of it's going to go into the air as it's slowing. When it actually touches down, some of it, you hear that screeching, but there's also the tires will heat up. The ground will heat up. So there's just lots of places for it to go. If in doubt, energy goes towards heat and sound. That's just sort of a catch-all. The heat part, sometimes textbooks will talk about the thermal energy. So 69, physics instructor demonstrates energy conservation by releasing a heavy pendulum bob, as shown in the sketch, allowing it to swing to and fro. What happens if he gives it a slight shove? Now, the whole demonstration there depends upon two things. One, it depends upon that he does not move his head. And so typically you do it with your head to the back of a board, because if you're out in the open like he is, you also have the potential of leaning forward, and that could really cause some damage. So you release the ball. You assume that the length of the pendulum is the same. So it starts out with no kinetic energy, all potential. The potential changes into kinetic, and it comes back. Because you are never actually going to break even, there's going to be loss somewhere. Usually there's a little bit of heating up, or it hits air or something like that. It loses energy. Therefore, when it comes back to 0 kinetic energy, it won't have as much potential as it started with which it started. And so if he gives it a slight shove, he's now added additional energy into the system. And so if he adds more energy into the system than is lost, then it can come back farther than he started. 72, a moving hammer hits a nail, drives it into a wall. If the hammer hits the nail with twice the speed, how much deeper will the nail be driven? If the hammer hits with 3 times the speed, and so forth. So the hammer has a certain mass and velocity. So if you double the speed, you basically are quadrupling the kinetic energy. The work that can, therefore, you have all this energy in the hammer, which can now do work, which will be force times displacement. So, and the reason why it quadruples the kinetic energy is the fact that you have, because the speed is, it's 1/2 mv squared. The v is squared. So if it's 3 times the speed, you now have 3 times, the 3 also being squared, and so it's 9 times the original amount of kinetic energy, so you can do 9 times the work. So for the same force where it hits the nail, you'll drive it 3 times as far. In reality, you probably are not hitting it. It all depends on how you do it, because there's a time factor in there also, but the essence of it is they want you to realize the speed is squared, and so if you double the speed, you quadruple the energy. If you 3 times the speed, then you'll 9 times the energy. 74. Why does the force of gravity do work on a car that rolls down a hill, but no work when it rolls along the level part of the road? Again, work is based upon force times displacement, and it's a dot product. How much of the force is in the direction of movement? So in the case of it's going down a hill, you have the car going this way and the force acting this way. Part of the force is down the hill. For those who've had some trig, it would be the weight times the sine of theta, where theta is that angle right there. When it's on a level part, the work is this way, but the level is this way, but try that again. The direction of movement is this way, but the force is that way. They are perpendicular to each other. Does not do work that way. Number 81, discuss the design of the roller coaster in terms of conservation of energy. Well, energy is, if they're starting at rest at the top of the peak, they have all this potential energy, then it goes into kinetic, gets however much transferred to kinetic, and then it's back into potential. So in this particular case, it looks like it's going to try to come back up to the same level where it starts and potentially go even higher. You can't do that. All the energy in a roller coaster happens when you go up that at the very top. It's all potential energy, and then the rest of it is you're converting that energy into kinetic and potential. They take into account the amount of loss, and so it, assuming that there's no depth issue right there, you're barely going to make it over that second hill hump if you do at all. 86, when the velocity of an object is doubled, by what factor is momentum changed? Momentum is doubled because it's just mass times velocity. Kinetic energy would be 4 times because it's the speed squared. 92, 2 lumps of clay with equal and opposite momenta have a head-on collision come to rest. Its momentum is momentum conserved? Yes. Equal mass colliding, boom. No total momentum of 0 beforehand, total momentum of 0 afterwards. Kinetic energy is not conserved, and that's just because some of it goes into the heat. There's non-conservative work being done. It's the normal force, which is non-conservative work. Therefore, energy is not conserved. And that is it for Think and Explain.